All right, good morning. Thank you. I'm from Chicago, so this is a very nice treat to be invited over to Sweden, to Stockholm, and to you guys won the football match last night. That was nice too. It was some beautiful soccer, or football. I'm sorry. So football, soccer, whatever. I love this rating system, the cards. Except for those of us who are colorblind, I just put one of each in there because. So they all look the same color to me. But anyway, so slight schedule change, but that's good for me. I get to go first, and it's quite an honor to go first. It's really great to be here, so thank you. It's really, really special. So we're going to talk about parallel programming, which is sort of my field. I'm an academic mostly, and then do a lot of consulting, mostly with Microsoft, but other companies as well. And high-performance computing, parallel programming has been my thing for 30-plus years, so. It's always fun to talk about. So the agenda is really just to sort of motivate this and then just dive in and do some examples. I like to code as much as I can, and I suspect most of you as well. So we'll talk about going multi-core. What is that about? I'm going to focus on C# and .NET, and then we'll talk a little bit about the hardware, and then obviously about the software. So we'll do some programming. I'll show you my top 3 patterns. The 3 that I think you should know if you don't know already, if you're going to do parallel programming from a performance perspective, and then lots of demos. So if all goes well, none will crash. So we'll see how that goes. Okay, so I just want to set the stage with sort of separate the two camps of sort of parallel programming. So there's the asynchronous side, and that's very, very nice nowadays because we have the async and await keywords in the compiler now, which make it very easy to do. But that's really about, from my perspective, responsiveness, making the UI not lock up. I need to do some I/O operations over the network, and I don't want to wait for those. So I want to do something asynchronously on the background. So that's really about GUI and cloud and Windows 8 and networking and things. That's not what I'm going to talk about. So what I'm really after is the other side, which is parallel programming for performance. I just want to get something done faster. So engineering, oil and gas, the pharmaceutical companies, all the big data and Facebook and social media. That's what I'm after, is to try to speed up, make that go faster. So that's the sort of motivation for today is performance. Now, the way the hardware is going, we all know what's going on. So from a hardware perspective, the way you get better performance is multi-core. So most machines now are dual core. Our phones and tablets are going quad core. So that's the way the hardware is proceeding. The hardware is going multi-core. Now, just in case you didn't know, why are we going multi-core? Basically, we couldn't speed the chips up any faster. So we couldn't make a single CPU go faster. So what we had, basically because of heat problems and just power problems. So if we could, we'd just build a faster chip. 8 gigahertz, 12 gigahertz, 16 gigahertz. The problem is the heat grows too fast and the power requirements are exponential. So we just can't build one chip that goes really, really fast. So instead, what we have to do is build simpler cores that go fast, but don't go, they're 2 gigahertz or so, 3 gigahertz, but we stop there. And the way we get better performance is we just put more cores on the chip. So that's really why we ended up here, is because of the heat and the power problem. So that's why the hardware went multi-core. We can't really build it to go any faster. So what that means for software, if you want your software to go faster, you're going to have to code for the multi-core. I studied in graduate school, and people are still working on trying to get the compiler to do this automatically, to just take your program and make it run faster by making it multi-threaded and multi-core aware, and it's a failure. So maybe in 20 years, 50 years, the compilers will figure this out, but right now, that's not really going to happen. So if you want better performance from a software perspective, you're going to have to use multiple threads and manage that yourself to one degree or another. So what we're going to be talking about today is some form of multi-threading, where we're going to have the main piece of code on a main thread, and then we're going to spin up worker threads to run other tasks. So we'll have worker 1, worker 2, and those tasks will run on the worker threads. The main method and maybe the UI is running on the main thread. And then basically you depend on the operating system to manage the threading. So they take the threads that they're getting created, and they manage them and schedule it on the cores. So basically our job is to sit at the top and create. Today what we're talking about is tasks, so we're creating tasks. And we leave it to the operating system to schedule this. And as long as you have multiple cores, the operating system is pretty smart, and it will run it on different cores and hence go faster, hopefully. So that's the idea. So in .NET, the programming model is called a task. So a task is just a unit of work, or an object denoting an operation or a computation. The nice thing about what .NET is doing, and others are doing this too, it's not just .NET, but what we're trying to do is separate the work from the threads. The threads are what actually give us the performance, because you get multiple threads going on the different cores. But what's really nice is to separate the concept of the workload, the tasks, from the actual threads that are running them. And so that's what .NET does, what other libraries do, is we separate those two concepts. So we don't have everybody creating too many threads. Instead, we just have creating units of work, and someone else manages the threads in the cores. So I'll be talking about, or at least demonstrating, the task parallel library. I'm not going to talk about the library. You can get that elsewhere. What I want to do is show how to use it and talk about how it works and show some patterns. So there's lots of ways to create tasks, wait for them to finish, way to get results back from the tasks. There's a way to compose tasks. There's higher level constructs to get parallel loops, which create the tasks for you. There's data structures. We'll talk about, and you'll see some of these things. So I'm not going to go into those in details, but mostly I'll be doing the latter, the parallel loops, and we'll look at the data structures too. So we'll see some of that. Okay. Now the way, if you've never seen the execution model, it's a fairly sophisticated model underneath. It's basically a little operating system in the .NET runtime. So down here we have our cores that are waiting to be used, where we run our threads. And the idea is what .NET's going to do is create a worker pool. So we have a thread pool down there, down here. And then this spans across the app domains. And we have the TPL, and then there's a scheduler in there that schedules the tasks onto the threads. And then we have a resource manager that's managing the thread pool. And then we have Windows, which is scheduling the threads onto the cores. There's a global work queue, and then each worker thread has its own local queue. So there's a global queue, there's worker queues, and then basically what I'm going to do is an example of a parallel loop. So when I do parallel loops, the parallel loop will spin up units of work. So it takes the loop and breaks it into chunks. And then those chunks get thrown into the global queue, and then eventually those work their way through the scheduler to some worker thread, and it gets put into the local queue. And then those, once those all animate over there, and then eventually those worker threads get scheduled, and the tasks are running on the cores. So that's basically what's going on behind the scenes. We have schedulers, global queue, local queues, and then tasks are pieces of work that are being distributed to the threads. So it's a fairly sophisticated model underneath, and we'll see a little bit more about that in a second. Okay, this is probably a good point. So I need my phone because my wife bought me this beautiful watch for my birthday. It's beautiful, except it's green, and I can't see green. So it's beautiful jewelry, and I can't read it. So I can't ever tell what time it is. So I have to use my phone to know what time it is. Color blindness is an interesting thing. But anyway, so I love it. I just don't know what time it is. Okay. It's pure jewelry. So let's do an example. So what I want to do is Mandelbrot. You've probably all seen this. The beautiful thing about it is it's very visual, so you can see the parallelism. So let's jump in there. So all this is on the. If you're interested in any of the code you see or the PowerPoint, it's up on the web, and I'll give you the link again at the end. So all these the code and things is up there. So I'm going to run Mandelbrot there. Okay, Control F5. All right. So there's actually some mathematics behind here, Mandelbrot set, chaos theory, all this, stuff. If I wanted to make it sound very, very lofty, but it draws really pretty pictures, which is what I'm after. But it also will help see the parallelism when it happens. So the nice thing, so what we're basically mathematically doing is each pixel is a point in space, and we're trying to see if it's in the Mandelbrot set or not. And if you see a light color, that means it was easy to figure out that it was not in the set or was in the set. And the dark colors are where it takes more computation to determine if it's in the set or not mathematically. And that takes about 30 seconds. Okay. So if we run it sequentially, it's 30 seconds. And then we can see that it's sequential by the, there's a single color on the right. So a single color on the right means a single thread is doing that. So right now I have a UI thread and a worker thread that's just drawing the computation. Okay, so what I want to do now is do this in parallel. All those pixels can be processed in parallel and see if they're in the Mandelbrot set or not. So what I'll do is just do that all as an entirely parallel computation. So get the namespace. And there's essentially, it's a doubly nested loop for every row and every column, basically for every pixel. So what I'm going to do is just go ahead and make all that fully parallel. So parallel loop, start at 0, do all up to but not including all the pixels in that row, and then turn the body of the loop into a lambda expression. So I'm just doing, hopefully you've seen lambda expressions before. Basically, I'm passing the loop body as a lambda expression of chunk of code. I'm passing that sort of a delegate into the parallel library. It's no longer a loop, so I can't break if it wants to be canceled, so I return out of it if the user says cancel. This is the inner loop here. We might as well do that in parallel too. Why not? Okay, fire it up. Okay, so the first thing we see is it's going in parallel. So we can see that there's multiple things happening at the same time. And we also see that it finishes much faster. So from 30 seconds to 4 seconds, 5 seconds. So it ran about 6 times faster. So obviously we're getting much better performance. And what I should do is show you my machine. So I have, so this machine's quad core, and then it has hyper-threading, which is usually mostly marketing, but it actually turns to help here. So what I have is 4 cores. It's a quad-core machine. The hyper-threading means that inside each core, there's basically 2 integer pipelines. So it can do 2 sets of integer-based threads at the same time. So if I'm doing all integer work, and this is integer work, I can potentially go 8 times faster. If you're doing other kinds of work, floating point, you're going to go at best 4 times faster. The hyper-threading doesn't pay off there. But to Windows, it appears that if I can do 8 things at once. So it's going to fire up 8 threads to do this. Let's just hit go again. So you can see the machine peaks out at 100% because all the cores are busy, at least until computation's up, and then they all spin down and we're back to idle stage. So, but one of the things to note about this, which is very interesting, because this is where you see the benefit of the library. Normally, when you do things in parallel, you normally just sort of break it up into simple chunks. Like a normal sort of naive way to go about this would be, I have 4 cores, let's divide it up into 4 sets of rows. So group 1, group 2, group 3, group 4. That would be the sort of naive, straightforward way to do this. It's easy to code that in parallel. The problem here is that technique doesn't work because this is all very light colored. And so the threads that would be dedicated to that would be done very quickly. And then you'd have 2 threads here in the middle doing most of the work because that's the dark color and that's where it's difficult. And so if you just do a straightforward static distribution of the workload, you don't really get much benefit because 2 of the threads will finish and those cores will go idle, and the other 2 threads are doing the rest of the work. So what you really want here, this is a case where you need dynamic load balancing. You need to have some way of breaking the work up, and then what happens here is the technique's called work stealing. So what happens is the thread at the top finished very early, and you can see that from the right. The band on the right's the yellow. So that yellow thread, when it was done, jumped in and helped out, or what we say, stole work from other threads that weren't finished yet. And so that's one of the nice benefits of some of these libraries is that they have a very smart engine underneath. So this person was done very quickly, so they jumped in and helped out in other places. So, and that's not easy to do, but that's one of the aspects of the library. So that's very nice. Okay, so some observations about this. One is that work stealing. So what happens is when one of those threads is out, when they don't have anything to do, they look in the queues and they steal from the back. So if there's some work in the other queue, they'll go over to their neighbor and take it out. Or they'll take a chunk of it and they'll do that. And if they get done, they'll go take more work from a neighboring thread. So work stealing is part of this model. Basically, the rule of thumb is 2 threads per core, 1 for computation and 1 for I/O. And then the system will spin up more threads as needed, for example, more I/O requests, or retire threads as the pool gets large and they're not doing anything. So that's what the resource manager is doing underneath, is managing the number of threads in the thread pool. So all that stuff happens automatically. I don't know if we take questions as we go. I don't know what the protocol is, but I'll pause for a second if there's any questions. That's normally what I would do. So, go for it. Question.
How does .NET know if your thread's in the IO thread or a computation?
Good question. It has no idea. So how does .NET know if it's a computation thread or an IO thread? It has no idea. So it's sort of your job to to keep track of that. So if you had like 100 IO requests, you can start firing that into the system. But if you're doing compute work, you would never create more than one thread per core, or you wouldn't try to overwhelm the system with too much work that's compute bound. But .NET doesn't know. So for example, if you have threads you have demands where this is something that's going to be long lived, you're supposed to tell .NET when you create the task, this is a long running task, and it dedicates a thread to that. So then it knows sort of more about what you're trying to do. Yeah. Other questions? Cool. Okay. Okay. So when you're doing performance work, how do you know when you're done? You're done when what we call linear speed up. So speed up is how much faster your program is running. The goal is what we call linear speed up. So if I give you n resources, or if I give you 4 cores, it should run 4 times faster. If it runs 4 times faster, then you're done. You can go home and watch more football or whatever it is you want to do. So that's sort of our performance target. So this is usually how the goal is, and you rarely attain this, at least for increasing number of units. But on the bottom there is your number of cores or your number of execution units. So if I give you 8 cores, what we hope it does is run 8 times faster. And 16 cores, 16 times faster. At some point this will drop off, but this is your goal. This is sort of what you aim for, and try to get as close to that as possible. Okay. All right. So let me do another demo. This is I know this is kind of boring, but stay with me because there's a good message at the end. Matrix multiply is like where everybody's eyes close, but I promise that there's a nugget, there's a gold nugget in a few minutes from now. So just bear with me. So there's a point to this because I know it's boring. It is. Okay, so matrix multiply, okay. We have libraries that do this. Why do we care? Because there's an interesting thing to talk about at the end here. But so matrix multiply, this is very parallel, right? Because you basically have to multiply for every row and every column. You multiply and add those elements, and you end up with a target result in matrix C. So there's a lot of parallelism here because you can compute all of these in parallel just by reading the rows and columns, multiplying and adding. So it's embarrassingly parallel. So lots of parallelism here. Now I'm going to run this on my machine. That's the die. That little image is the actual chip die for this laptop. So that's my quad core logic that flew in there. So that's what I'll use it on this machine. So this is the naive approach. So if you know anything about matrix multiply, don't give away the secret. But I'm going to do the naive way first, then I'll do the correct way second, and that's where the nugget will appear, the good information. But basically, it's a triply nested loop. So for every row and every column, so for I and for j, for every row and every column, you multiply those rows and that row and column together. So the outer loops are the row and column. So that's for every row and every column. And then what do you have to do with that row and column? You have to multiply and add. So there's a loop that multiplies the row and the column, and then you end up with a target result when you're done. So row, column, result, row, column, result, row, column, result. So that's matrix multiply. I love it with my students, the intro students. The first time they see triply nested loops, they just melt onto the floor, and they're like, you can't possibly do that on a computer. I'm like, no. So great stuff the first few times. You guys forget what it's like with those little undergraduate minds, then you see stuff like that. Anyway, okay, so what we're going to do is do this in parallel. This is really our first pattern, and this is by far the best pattern, the safest pattern for parallel programming. This is called structured parallelism or fork-join parallelism. Basically, what you try to do is keep your program as sequential as possible until you need parallelism. So you think of your program sequentially, because that's normally how we think about programs. You go parallel when you have the workload, and you go back to sequential when you're done. So this is called structured parallelism. It's only parallel when you need it, and then you go back to sequential because that's just a safer, easier way for us to think. So this is a very good way to program, at least if you're new to parallel programming, this is the sort of standard way to start. And this is kind of how a lot of things in the .NET library work. So they do what we call is structured, or the old school fork join from Linux, fork join parallelism. So what I'm going to do is do what I just did with Mandelbrot. I'm going to do a parallel for loop. And the parallel for loop follows this pattern. So in other words, when you say parallel.for, it forks off and does a bunch of work in parallel. When that's actually a method call to the library. When that call is over, you're back to sequential code. So basically what we're doing here when we use this type of approach is it's sequential code until you hit this. Then it goes parallel through that body of code right there. And then when you hit the end of the loop, you are back at sequential code. So it's only parallel for that region of the program, no more, no less. So that's called structured parallelism. Okay. So matrix multiply, the most boring example there is. It's good, there's something good at the end. All right, so let's run it first. Full screen. Anyway. All right. So there it is. There's the triply nested loop, the naive approach. Control F5. It'll run for 30-ish, 27 seconds, I think. But I bumped, so you can see the matrix size is pretty big, 1200 by 1200. So you got a couple million elements there. So it's a pretty big matrix. They're all real numbers, they're all doubles. So it's fairly intensive from the hardware perspective. And it's running on one core. So this is still the sequential version. Okay, cool. So 27 seconds. All right. Now the library makes this easy to parallel. Again, this is embarrassingly parallel. I can do it all in parallel. So then what you do is you go to the outermost loop and you make that parallel, which makes basically everything parallel. So I go to the outermost for loop, parallel.for, start at 0 for every row, pass I as a lambda expression into the loop body. Thank you. Oh, the library is also missing. Let's get the namespace. Okay. Okay, happy. All right, so we're doing a parallel loop, passing in the loop body as an argument to the library. So all those iterations will be done in parallel now. Control F5. So 27 seconds, we're looking for, I got 4 cores here, 4 times faster, so we're looking at 7 seconds. Right, okay, so 7 times 4, 28. So that's about right. That's linear speed up. So I have 4 cores, it ran 4 times faster. I'm done, I can leave, I'm done work, I go home, right? I think, okay, I've achieved my performance goal. So that's normally how we think about these things. If it's 4 times faster, 4 cores, you're done. Let's do that one more time. Okay. So we can see it spin up to 100%. It looks like it's trying to use all 8, but again, the hyper-threading doesn't work here, so that's why it's only 4 times faster, not 8 times faster. If these were integer matrices, it would probably be 8 times faster, because it would be able to use the hyper-threading. All right, so remember that number, 7 seconds-ish. Just keep that in mind. Okay. Okay, so here's the nugget from the boring example. So, but wait, am I really done? Or, so I'm 4 times faster, but am I really done? So what is the other half of the chip? Cache, memory. And it must be pretty important because it's the other half, right? If it wasn't important, it wouldn't be there. So it's like, they dedicated the other half of the chip to this stuff. And so the question you have to ask yourself is, are you actually using it effectively or are you not? Because if you're not, you're wasting the other half of the chip. So that's a pretty large real estate if you're not using it effectively. And what I'm going to show you is we're not using it effectively. And if you so we need to use the other half as much as we use the cores. So you have to always think about the other half. The problem is it's hard to think about because the tool support's not really there, at least to help you very effectively. But let's look at the other half of the chip. So let me demo this again and do it the cache friendly way. So what I'm going to do is rewrite this to use the other half of the chip. So here's the issue. If you know anything about, so people who do matrix multiply, they already know this because this stuff is well known. But if you're doing matrix multiply, you never ever write the code this way. And the reason is the column processing is bad. It's bad because of the way the hardware works. So this is part about knowing how the hardware works and then taking advantage of that. We know it has multiple cores, so we write multi-threaded code. But you have to take advantage of the cache too. The reason this is bad is the way the caching hardware works. So the first thing you have to understand is the chip is so fast and memory is slow. And I'll give you some numbers in a second. But basically, if the CPU has to wait for things from memory, it's like driving down the Autobahn and just putting the brakes on and waiting for a while and then starting back up. I mean, the CPU just crashes and burns while it waits for things coming from memory. So what happens, so one way to sort of minimize that wait time is that when you go to memory and read something, such as an element of a matrix, what the hardware will automatically do is grab the people to the right. So it grabs a piece of memory and it grabs its neighbors to the right, thinking that what you're going to do is go to this neighbor in the next operation, the next iteration of the loop. So the hardware is thinking you're going to the right. And if you go to the right, then the next thing you need will be given to you very quickly because it was brought from memory with the other piece of data. So this is how caching works. You grab a cache element, you grab a cache line, which is a bunch of elements, one and its neighbors. Now what we're doing here in matrix multiply is going down so that when the hardware grabs the neighbors to the right, we don't use them, we ignore them. And so we're not using the caching effectively because it's bringing stuff into the cache and we're throwing it away or we're ignoring it. So what we want to do is rewrite the algorithm to go across. Mathematically, it's the exact same algorithm. It's the exact same number of computations. It's just that we do them in a different order. We do them across, so we do partial computations instead of doing it all at once. So all we're doing is just doing things in a different order. It's the exact same algorithm, just a slight change in the way we do things. So the painful part for your head is when you see this, what you're going to do is the solution is called loop interchange. And the compilers will do this if you tell them to. They just invert two of the loops. By doing that, all I'm trying to do is change this. So let me jump back for a second. Let's see if this is the one. Yeah, okay. So this is the bad one. Okay, so this is the bad way to do it. If you look at the bad one, the loop is on the variable k, and that's this index here. If k is changing, that's changing the row that you're working on. So if you let k change most frequently, that's the row index. So that means the algorithm proceeds down the column because it's changing row, 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 row. So we don't want that. That's the bad algorithm. So that's, bad. What we want is the love. We want the goodness. So the goodness is to go vertically, to go across the row. So what we do is we interchange the loops. So the innermost loop is now j. So it's ikj. And then j is the column, so when you change j, it goes across. That's all we're going to do is just know that by changing this, we're doing better caching. The really amazing thing so how much of a difference does this make? So that's the fun part to demonstrate. So what I'm going to do is invert these two loops. And just trust me that it doesn't really break anything. And there actually is code underneath checking. So if we do break matrix multiply, it checks to see if it's still working. So that should startle you, right? It was 7 seconds before. Now it's 10 times faster. It's actually faster than it was with the multi-cores. That the caching is as important in some cases as the actual multi-core processing as well. So that's how important the caching is. And this problem is getting worse. The more cores you have, the harder it is to feed the cores with the data they need to run fast. The cores can't run without the information from memory. So the caching is a huge part of this. And that's why it's easy to have 2 cores, 4 cores. To have 8 cores is very difficult. They can build it. It's easy to build. The hard part is how to get enough caching to feed the beast so that it runs fast. So that's the nugget. That's the important part. So the important part of this is there's a huge factor of improvement here. But how do you know this? You have to know your algorithms. You have to know how they're using memory and how they're accessing things. Question? So the observation is we're doing 2 levels of indirection because it's double indexing. I leave it to the compiler to reduce that itself. So most compilers will hoist that and say, okay, you're working your way through an array. I'll just grab a pointer and then bump pointer plus plus. So that should be handled by the compiler. One thing that it's a good thing to test, because if the compilers don't do it, then you should write it yourself, because you don't want to have to keep doing row times column to access elements. Most compilers will just turn that into pointer arithmetic underneath. And notice but that does bring up the point. Notice I didn't do it this way. Row, comma, column. There's 2 ways to do 2-dimensional matrices. If you do it that way, there's an actual method call to array.get. So I left them as what we call jagged arrays, where it's rows and rows point to column vectors. Much more efficient this way. Other questions? Okay. All right, so this is a little bit more about knowing your hardware. So the multi-core architecture, I'll just run through the terms. So sockets are the actual chips. The sockets are like the thing with the pins. So this sort of diagram here is implying that there's 2 processors. So those would be 2 different sockets. And the sockets can actually have multiple cores. But the caching is the part that's new. Most machines have 3 levels of caching. So each core has its own cache to feed the core as fast as it can with data. And then each socket, so all the cores together on one socket will have a level 2 cache. So that's feeding all the cores on that socket, that chip. And then you might have a bunch of sockets or a bunch of chips. There's a level 3 cache, which is feeding all the cores across all the chips. And then you have the really slow RAM sitting way over there. Basically, the cost of this is roughly order of magnitude. So you pay to get something from the level 1 cache is 1 cycle. So the CPU has to wait 1 cycle to get something from cache. Level 1. Level 2 is 10 cycles. Level 3 is 100 cycles. Level 4 RAM memory is 1,000 cycles. And that's kind of more or less just a rule of thumb. But it's a factor of 10 wait time for every level of cache you have to go out to get data. So going to main memory is incredibly slow. It's 1,000 cycle penalty every time you do that. And that's why matrix multiply is so much faster when you do the caching properly, is because basically the data moved from here to level 1, and then it runs much, much faster, as you saw. Question? Right, so good question. So why don't we make the whole machine be a level 1 cache? Which is a great question, why not? So it's faster because it's of its proximity. It's actually right there on the chip, but it's very expensive to build. So to make it go that fast is very expensive. You can't afford to buy a machine that would have all the RAM behave like that. And I don't know if you could build the machine you can't practically build a machine to do that. So level 1 caches are usually 32K. They're very small, very expensive, and they're right on the chip. So one of the things, what's the difference between this chip and this chip? Why is this chip $400 more than this? It's the same cores, but it's all the caching. This chip will have more cache if it's more expensive. That's the expensive part now. And you just can't scale it up. Right. So that's the best we can do for scaling is level 2 is fast, but not as fast, it's cheaper, and so on down the line. Yeah. Right, so the observation is if we actually look at matrix multiply, it was more than linear speed up, because if you add in the cores and the caching effect, it ran 30 times faster. It went from 30 seconds to 1. So that's called superlinear, it went faster. So there are some algorithms where, so the observation is, if you run something sequentially, you basically are limited by just those caches and running that fast. As soon as you can break the problem apart to multiple caches, you can now get faster speed up because you can take advantage of more things that are closer in memory. So you do see that on rare occasions, that things run even faster than linear because you can take advantage of the extra caching and things like that, that they wouldn't otherwise fit in that one cache. So that does happen. You're a superstar if that happens very often, so. Matrix multiply is the only one I can do that makes it work like that. So one more question. Go for it. Yeah, so how much is it'd be about the same thing, 10 times faster. So so his question is, if we just take the sequential code, forget about the multi-cores, and just use the caching, it'll run about 10 times faster. You'll see about the same benefit. So the caching will get you from 30 seconds to 3, and then the multi-core will get you from 3 to 1, or 30 to 4, and then 4 to 1, yeah. Yeah, so the caching and the cores are orthogonal. You can take advantage of both or one or the other. Right. So even sequential programs, you should worry about caching. Well, okay, and we can actually demonstrate that when we just go back. So this is the sequential program, but yeah, 2 seconds. Wow, faster than I thought. So it's 15 times faster just from the caching. I don't show that first because it's not as impressive when you put the cores on. Yeah. So thank you for ruining it. Yeah. Good on you. All right, okay. Cool. Can't look at that. All right, look at that. All right, we good? Okay, so high performance computing, so this leads me, this is one of my favorite little equations. So I work in the field of high performance computing. That's sort of the umbrella for this sort of idea. And then the equation I like is when you work in this, if you're trying to make something go faster, parallelism is sort of part one. You got to expose the parallelism for the cores. But the other thing you must think about is the data locality, right? How to get the data you need into the cache so that it works faster. And the farther it is away, like networks and hard disks, the harder you have to work to get it into the core and the caches. And then you have to also worry about contention, the threads interacting with each other. We'll see some of that in a second. So you also have to subtract out the contention, eliminate contention, which is, for example, is often locking. Locking is bad because then things that are parallel go sequential. So we have to subtract that out of the equation as best you can. Okay. So just a couple implications of some of this. If you have really elegant code with lots of layers of abstraction, that's usually bad from a parallel perspective because it hides a lot of things. So this is sort of like anti-good engineering is parallel programming, because you have to reveal everything so you make things as parallel as possible. So often you have this really elegant design that you got to rip apart and smash it all back together. So you get all the loops right next to each other, you get all the data right there, then you run it in parallel. So there's this notion of anti-abstraction so that you can reveal the actual guts of the algorithm right here so I can make it parallel. And then another thing is this bit about caching. You know, most programs are very elegant. We have object-oriented collections. We have collections of objects. But suppose we're going through this collection, and all we want to do in parallel is hit a particular field of an object. So we're iterating through this collection, but we're just touching these fields, x1, x2, x3. What happens is when you touch the object, you're going to bring into the cache all the stuff about the object. You don't really want that. When you go to when you hit something in memory, when I hit this object here, what I really want is these things waiting for me when I hit those. I don't want the other, pieces of data that's in this object, because I don't need that. What I need is that, and that. So sometimes you have to, quote, flatten your data structures, which is if you're trying to do stuff in parallel and do it fast, you don't want elegant arrays of collections of objects. You want raw data in arrays that you can iterate through quickly and that the caching hardware can effectively use. So unfortunately, a lot of the stuff we do in parallel programming is take these really beautiful programs and destroy them and make them fast, but not as elegant as they were design-wise. So that's just sort of sometimes the side effect of this. Okay, so that's structured parallelism, a little bit about the hardware, a little bit about the software. What I'd like to do is show you some other patterns that you should know about. So my top 3, structured parallelism was 1. Let's look at reductions and then producer-consumer. So these are the other 2 that I think are very useful. So the idea of a reduction it's a very simple idea. You've all done this, whether you called it a reduction or not. The idea of a reduction is to take something and reduce it to a single value. So I want to sum up a vector of numbers. I want to find the minimum. I want to find the maximum. These are all reductions because we're reducing to a single answer. And so in this, the little example I'm going to be doing here is I'm multiplying. So I'm multiplying 2 elements, and then I'm multiplying 2 elements, I'm multiplying 2 elements, I'm multiplying 2 elements, and then I'm summing all of that up. So my end result is a sum of all those multiplications. So that is technically termed a reduction. So the naive way to do this, so there's a sequential code. So it's a for loop that just multiplies and adds. So it's sum equals sum plus, right? So we're just summing up all those multiplications into a single answer. Now the first thing is if you do this in parallel, that's a race condition because you have a single variable being shared in parallel. So the naive way to do this is to recognize that, oh, okay, there's a race condition here. So what I'm going to do is put a lock around it. So what I'm going to do is every time, so if I do this in parallel, I have multiple accesses in parallel to the sum variable. That's not allowed because it's shared memory. So what I need to do is lock something so that only one thread touches that shared variable at a time. So I throw a lock in there, but that's contention. Every time you have locks, you have contention. That's not going to run at all fast because you're going to have all these threads multiplying and then they're all going to wait for each other to add it to the global sum variable. You can get a little faster if you use interlocking. Interlocking is hardware locking. So the lock statement is software locking. The interlocked, if available in the hardware, uses hardware locking. It's still very expensive because it's still a lock. So all of these things are slow. Sometimes you have to use locks, but you try to not use them if you can get away from it. So the idea here is there's very easy solutions to solving reductions. So what you want to do is redesign the code, not just throw a lock in. So this is the way to do this in .NET. I wish it was prettier, but again, here's the idea. So conceptually, what we're going to do is just break it up into parallel pieces and compute partial sums. So what we're going to do is have one task or one thread do this chunk here, and then we'll have another one do this chunk here, and then we'll have another one do this one, and we'll have another one do that one. So it's not rocket science. We just have them compute partial results. So instead of everybody updating the global variable and locking to do that, what we do is everybody just work on your own local variable or p-sum, partial sum. And then when we're done, after we've done the join, so the fork is do it all in parallel, and then what you do is join, so now it's all sequential code. Someone adds up the partial sums and computes the final answer. So what we do is we do everything in parallel, but everybody computes their own local variable, their local sum, and then we reduce it to a single variable later, and then we have the global final answer. So we get rid of the global variable until the very end. And maybe the main thread can zip along, add up the partial pieces, and compute the result, because that's easy to do and fast. So that's a parallel reduction. Break it into local pieces, and then sum it up when you're done. Okay. So how do we do this in .NET? I wish .NET had a more elegant way to do this, but once you've seen it a few times, if you haven't already, you get used to it. But the key thing here is I need each task or each thread to have its own local sum, partial sum or p sum. So the way we write this in .NET is we're going to use thread local state, and we're going to use a different form of the parallel loop. So the parallel loop basically has, before what we saw was, show me the iteration range, and here's the body of the loop to execute. Now what we have are two more lambda expressions, two more things to initialize the local state and to do the summing of the local state when we're done, the actual reduction at the end. So let me show you what that looks like. So we have a parallel for loop, and this int is the thread local state. So int here refers to the thread local state. So what I have is an integer that's local to each thread. And the idea is, what will happen is .NET will sort of say, okay, well, every time we do an iteration of the loop, I will give you the thread local variable. You can add to it and then return it so it can be passed in next time. So basically, there's this local variable that each thread will have that cycles in and out of each loop iteration. And so now each thread has a partial sum. So the thing to notice in this code is there's no locking and there's no global variable. Every thread or every task is going to work on a local variable to compute its local sum. And then what we have is we have to have some way to initialize that variable, so that's going to fly in at the top. So this overloaded method has an extra sort of constructor or lambda expression to initialize the thread local variable. So I have basically a little lambda expression here that says initialize local variable to 0. So that kicks off when the thread starts or the task starts. So now everybody starts with 0 as their local sum, and then it's basically going to be iterate through here, and everybody's going to compute a partial sum of their piece of the data, of the vectors. And then when we're done, this last lambda expression is triggered when the reduction is supposed to happen. So as each thread finishes, okay, you're done your part of the computation. What you now do is take your partial result and add it to the global sum variable. So this is where we do the reduction part. Take your value, add it to the sum. Now this can actually happen in parallel. We can have multiple threads complete at the same time. So we do need a little bit of locking here. So what I'm doing is saying, take my partial value and add it, or interlocked add, which is a hardware lock, add it to the global sum. So this is the only place we need locking right at the very end, which is only going to happen at most one per thread. So very, very minimal locking, very minimal contention. So this is how you do a reduction in .NET in the task parallel library. Not a very elegant syntax, but that's the concept. So when you do things like min, max, sum, things like those kind of things that come up a lot, this is the approach to take. There's minimal locking here. Okay, so let me show you an example. So let's do a real example. I like this little demo. At least it's real. It's not like matrix multiply, which there's libraries that do that for you. So this is a funny little backstory because so Netflix, this is an actual competition. This is probably 6 or more years ago, maybe longer. I'm getting older, but maybe 10 years ago. I don't know. But Netflix had an internet contest for $1 million, I guess million US. They put out a data set and said, come up with a better movie rental prediction algorithm than we have. If you can beat our algorithm, we'll give you $1 million. And they awarded the $1 million eventually to some individuals who came up with a better algorithm. The interesting part was they got sued because they thought the data was private, but it's not private because people just looked at the data and then figured out who was each person in the data set. Oh, that person did 4,000 reviews. That must be Susan over there. So it was not really anonymous. So they got sued and had to pull it off the internet. But there's this very nice data file. What I'm going to do is mine that for the top 10, the most active movie reviewers. So I'm going to analyze this file and figure out who is the top 10 users of Netflix who are submitting reviews. So for example, user ID 305344 submitted 992 reviews. So maybe what we do is target them, we send them flowers, we do something nice to keep them reviewing movies, right? So we analyze the data, pick out top 10, and we give them free credits, or we do something to encourage them and thank them for all the reviews they're doing. So this would be a common sort of data mining problem. Okay. Now, very easy to solve this problem. The simplest way is just to create a dictionary. So what we're doing is we're going to mine this data file, and basically we're just going to count up reviews. So for every user, okay, here's user 944, count, oh, they did a review, count it. So user count, user count, user count, user count. Very nice use of a dictionary. So what we do is we just grab a movie review, and we parse it, and we figure out what user that was. That's all we need really is the user. And so what we do is just count how many times that user has reviewed a movie. How many times does that user appear in the file? So a dictionary is a great way to do that. So what we have is a user ID, and we have a count. And we just keep track for every user, their counts. And then we just get the top 10 when we're done. We sort it and grab the top 10. So it's a very easy problem using a dictionary. So the first time we look in the dictionary, if the user's not there, so the first time that they review a movie, we add them to the dictionary with a count of 1, because that's the first time. If the user's already in the dictionary, so that's another movie review they've done, and we just add 1 to their count. So we look it up in the dictionary, and we add 1 to that, and now they have 2 reviews, 3 reviews, 4 reviews, 5 reviews. So that's the idea. But the point here is there's a lot of these data mining, big data stuff kind of problems. Here's a way to approach these kinds of problems is the idea. So, all right. Let's fire up the demo. So let me just show you what the file looks like. It's most of these big data problems are just text files, right? Just raw text files underneath. And if I remember right, I think, no, that must be the user ID. User ID and rating, I think, and there's the date, and that's the movie. The movie ID, that's movie 1, whatever that is. User ID 1488844 gave it a rating of 3, average. So it's a big giant file like that. The original file is 2 gig, so it's a great problem to play with. This file is not that big. It's only 100 megabytes or so. Okay. So there's the main loop of the whole program right there. Just open the file for every line, parse it, and count it. And I think it runs about 8 seconds. So our goal here is to speed this up. That's our goal, right? Let's see how we're doing. Great, 8.6. So these are the top 10, and then 8.6. And if you're careful, you run it 3 times. Take the average. So we'll run it twice. We'll live dangerously. But 8.6 is about right. Yeah, okay. 8.3. So it's a little faster a second time. All right, 8 point something. Okay. So first thing is, let's see what happens if we just do it in parallel. Oops. So do I have my namespace up here? I do. So it's already ready to go. Okay. Come on, Joe. So for each thing in that collection, we pass the line to the body of the code. Okay. So again, I'm calling into the library, passing the loop body to process that line of the file, and then just do this in parallel across all the lines. Okay. Now it should blow up. See, that's what's frightening. What's frightening is when it actually, okay, so you might say, look, it ran in 3 seconds. That's really cool. Okay, but the results are wrong. I know that the top one's supposed to be 944, and it's not. It's some other number, but it should have blown up. But this is what life with parallel programming is. Even though the code is wrong, it's wrong because I'm using a dictionary, which is not thread safe. So I have a dictionary object that I'm using in parallel now, and it's not safe. If you read the documentation, it says, this is not thread safe. So you're not supposed to be able to do this. It'll do its best it can. It didn't crash, but the results are incorrect. So it's more fun when it actually blows up. All right, so let's just to convince you, right? So that's 981, so I got 981 that time. It's fast, though. Oh, there we go, cool. All right, so what I was hoping for this was when you have multiple threads that are in there playing with the dictionary, it's not thread safe, there's no locking or anything. And so eventually you corrupt memory and it blows up. So I was hoping for the blow up. But this is one of the things about parallel programming. When you get it wrong, the system's not going to tell you. So that's an important message if you're not aware of that. You can make anything parallel that you want. The compiler is not checking. They just don't check right now. This is hopefully something that will change over time. But there are easy errors here that they could check, but they don't. They don't know if the dictionary object is thread safe. The compiler doesn't know that. It should, but it doesn't. So it says, hey, you want to do this in parallel? That's fine. It's our job to know if it's safe or not. This is not safe code because that dictionary object is not designed to be used in a parallel way, even though it ran successfully. Okay. So one way to fix this, the naive way to fix this is we could lock and run it. So locking will fix it because what I have is a shared variable, and so one way to oh, that's not okay. Did that? Oh, is it 992, not 944? Is it 992? Okay, thank you. I was about to have a little problem up here. Because it should work. It's got locking in there, so it should work. What I'm surprised at, actually, is that I was expecting it to be slower. Because basically now you have all these parallel threads that are all fighting to get access to the dictionary. So even with the locking, it still runs actually faster, not bad. I was expecting it to run the same or slower. We start off with 8.3, 8.6 seconds. We added a lock, which should add a lot of contention, but what that basically means is it's not as bad as I thought. The parsing is taking enough time so that the threads are getting sort of out of sync with each other, and so then when they lock the dictionary, they're not all fighting for the dictionary all at the same time. But I'm surprised by the fact that it ran as fast as it did. But more importantly, it ran correctly, so 992, okay. Yeah, all right, 992, thank you. Okay, all right. So let me jump over here a second. So I jumped ahead of myself. So when you have shared state. So this is an example of the dictionary is like our sum variable. We have shared state. When you have shared state, there's usually 3 ways to fix this. You can add locking, which is what I just did. The second way to fix it is to use a thread-safe data structure. In other words, use a construct from the library where someone else did the locking for you. Those folks are professionals and usually do better locking, less locking than we would use by just putting a lock around the whole dictionary. So when you can use a library that's probably done it better than you have by just slamming a lock around it. So what I'll do next is the concurrent dictionary. We'll see if it's any better. But as possible, what you want to do is get rid of the contention and then use a reduction. So even though this is not a simple variable, it's a dictionary, what we could do is do a reduction, which means break it into independent dictionaries and then merge the dictionaries at the end. So that would be the best way to do it, which is get rid of the common shared dictionary because it's contention and that will slow you down. So that's what ultimately I want to do. And the most preferred is to eliminate the contention. Reduce it separately or reduce them into parallel activities that you reduce at the end. And that's the only contentions at the end. So version 1 was the locking version that I just did. And I would basically say, now, I was expecting it to be slower. Anyway, okay. It wasn't slower, so it actually did okay. But I normally would say that's not going to work. Don't even bother going there. I would never even think, I would just skip this step. Throwing locks around things is usually performance, just a killer. So the second version is to use concurrent dictionary. So the concurrent dictionary was designed to be used in a parallel way, and what they've done is they've redesigned it so it can be used safely in a multi-core, in a parallel environment. So then what we do is we switch over to concurrent dictionary, and then we have to change the API is different because the API has to work in a parallel way, and so you have to basically you have to search and update or add at the same time. You can't, basically this is an unsafe pattern here because you do the search first and then you update or add, and you have to do it all at one step. You can't do it in 2 steps. You can't search because you can have multiple people searching at the same time. They could both say, oh, it's not there, and they both could add it. So you can't break it into separate steps. You have to, in a parallel world, it has to be 1 step. So they had to change the API to be add or update. All right, so let's see. All right. So this is the locking approach, what, 4.6? Uh-oh, I got to speed up. Okay, 4.5, all right. So concurrent dictionary is the one I want to use. And luckily, when I switch over to the dictionary, it warns me that I'm going to get an error basically saying this API is no longer supported. So you have to do this differently because you have to do it in a way that is safe in parallel. Add or update. So the key is the user ID. The value, if they're not there, I want to add the value of 1. If they are there, then I am given a key value pair, which is the user ID and the count. And then I have to say, what do I want to do if they're there? I want to return count plus 1. Okay. So now what I've done is I've used the preferred approach, or at least this is better than locking. Oh, I kept a lock. Well, that was pretty stupid. Thank you. Double locking. I'm paranoid. We got to get it extra safe. Thanks. Then I really would have confused. So this should be a little faster. Okay, so it is faster, which is what I would expect. We're using a system that does less locking, it does more efficient locking, so it should be consistently faster than anything we do ourselves. Right, so it's consistently faster, about 4 seconds. Not a lot faster though. I was expecting it to be better. Okay, cool. All right. Okay, so that's better than the previous approach, and so I'm a little happier. A little smiley face comes in there. So that's not much better, but it's slightly better. Okay. The last one is the reduction, though. So what you really, if you can redesign the algorithm, that's where I introduced the pattern of reduction. The idea of the reduction would be, so we saw this pattern where you have to basically jump. This is the part we care about in the middle here. So what we now do is break the loop body so that we have each thread, each task, is going to have a local dictionary that it works on. And then we'll merge the local dictionaries into the final dictionary at the end. So we do the reduction at the end. So the idea is, how much faster is this? So what we'll do is have each thread do local dictionaries, which means that in the initialization phase, so when we start up, when each thread starts up, it creates its own dictionary in thread local state. So every thread has its own dictionary, and then the end, when the pattern is over, or when the threads are joining, when the parallelism is over, what you have to do now is lock the dictionary and merge the results from the local into the shared one. So the locking happens at the end, but not during. So this is, again, the reduction pattern. Do it in parallel and then reduce at the end to minimize contention. Normally I would code this up in front of you, but since we're running out of time, I will just run the parallel version. Now I'll show you that there's a lot of versions of this. If you're interested in this example, I did a whole bunch of different ways to see which was the fastest. So there's a whole bunch of examples there, and I'll show you one more before we're done. But this is the reduction, so let me run this one. Okay, so actually not that much better, but we're getting a little faster. So we went from 4.6 to 3.5 by trying to eliminate the contention. 3.5, okay. So we've knocked another second off, but I was hoping for more improvement, but okay. All right. Yes? Yes. Yeah, so the question was about the work stealing. So the work stealing is always going to be sort of happening underneath. So in this case, it won't really be necessary because, yeah, it's the workload for each thread is just that simple little line of code, the one review from the movie and parse it. So the threads will pretty much stay in sync in this case. But if one thread for some reason falls behind, other threads will steal some work from those. Yeah. So it's always there underneath the scenes. Question in the back, go for it. Right, so this is where we're going next. So the observation is, why don't we get the I/O out of the equation and see what that has to do with it? And part of this thing, part of the message here is, and I have to finish up because they're going to pull me off the stage in a second. But as first speaker, I get to do what I want, so I'll do what I want. I don't really. Yeah, so why don't we try to, you have to experiment a lot. So a lot of this is experimenting and see what works and what doesn't. Unfortunately, there's no good tools to say, you should always do it this way. So we'll experiment. So this brings us into the third pattern, which is producer-consumer. And I/O is a great example of this. I/O is very unpredictable, especially if you're going over networks to the cloud, things like that. So the producer-consumer pattern is a very good pattern for unpredictable workloads that involve I/O. And so a good thing you try to do, which is exactly what the question was about in the observation, is you try to separate the I/O into these other threads, and we call them producers. And the producers will do the I/O and put the information into some data structure, and then the consumers are pulling stuff out of that data structure and processing it. This is a very well-known pattern, and it's very good for unpredictable workloads. So producers generate, and the consumers process. So now, to do this properly, it's a little difficult to do because normally the data structure in the middle is not infinite in size. That's kind of unrealistic. So you have to have a data structure and you fix the size because that's just practical. And then that means if you have a fixed size data structure, what if it fills up? If it fills up, then the producers need to wait until there's space available. And what if it's empty because the producers have fallen behind? The consumers have to wait until there's something in there to process. So it's actually quite difficult to actually get to code this properly because you have to block the producers and block the consumers if it's full or if it's empty. The good news is there's something in .NET to do exactly this. It's called a blocking collection. What it does is make people wait if it's full and make them wait if it's empty. So this is just, so I'm gonna have to do this quickly, but the basic idea is you create one of these blocking collections. And this is also an example of where we have a tasks factory because we want to create, or at least we want to tell .NET that we are creating long-running tasks. So that what it'll do is it will dedicate threads from the work pool. It will create new threads just for these tasks, so that it leaves the other threads in the thread pool for short-term tasks, I/O requests and things. So we use the task factory, create long-running tasks here, and then basically the idea is you create one or more producer tasks. And these producers, so notice I'm using the task factory to do that. So TF is the task factory. And then what I get are long-running tasks. And what I do in the producers, all the producers do is the producers just add work to the queue. add as fast as they can, doing I/O, putting stuff into the queue as fast as they can. And then when they're done, they tell the system they're done. The consumers, what do the consumers do? The consumers just loop and keep pulling stuff out of the queue. So they just take. They just greedy. That's exactly what, greedy algorithm. So they just take stuff from the work queue. If they get an exception, then basically that means the queue is empty and they should stop. So they might end cleanly, or they might be blocked waiting for something, and then the queue is now empty and the workload's done, and so then they get an exception, meaning they should stop. So that's the basic idea of the producer-consumer pattern. Great for unpredictable workloads. So let me run my 2 demos, and then we'll be good. Thank you, Anders. Okay. So this is what it's going to look like. Let's just run it. So I'm sorry, I knew I had a little too much material, so it's always good to have too much than not enough. So version 1 said the producer's just reading from the file, putting into the data structure. The consumers are just pulling out of the file and processing. So there's one producer and a bunch of consumers. So it doesn't work very well if you just sort of have one producer putting things in and a bunch of consumers pulling stuff out. So that didn't work because it ended up the units of work in the queue were too small. What I'm doing is putting one line into the data structure. And what ends up happening is there's too much contention for that data structure because there's only little chunks of work in there. So it doesn't run very fast if you just sort of use it naively. But if you sort of say, okay, so what we should do when we do producer-consumer is we should batch the work. We shouldn't just put one unit of work in there, but we should put a chunk of work into the data structure. So what I have now is a producer that's putting in sort of more chunks of a block. It's putting units of work that are 1,000 reviews. So it grabs 1,000 lines from the file, puts it in the data structure. It grabs another 1,000 lines, puts it in the data structure. So it's giving the consumers more work to do, which means less contention for the data structure. So once I kind of fine-tune that, now we see that the time is pretty good. So now this is the fastest approach, but I had to fine-tune how the pattern was applied. So again, experimentation. Okay, so the producer-consumer ends up being the best way to go about it because, and generally with I/O involved, it's a good pattern to use. Okay, so that's best performance. So I will finish off with other things you should know about. P-link, parallel link, if you like link. So there's a way, this is the code in link. The beautiful thing about p-link or link is it turns a link query into parallel link query. So you do the dot as parallel. If you stick that into the query, everything that follows it will be done in parallel. So this is if you use link, you can experiment with parallel processing by doing as parallel. So what happens is all of this is done in parallel because I said as parallel as part of the query string. And so you can play around with p-link. So if you're using link, experiment with that if you want to go multi-core. So that works pretty well. It doesn't do any. It's about 3 or 4 seconds. So it doesn't beat any other ones, but it's not bad. So it's if you have link, it's very easy. Just throw it in there, see how it does. The other thing I'm really a fan of is functional programming. So if you're a fan of functional programming, or you need a reason to learn functional programming, is parallelism. The beauty of functional programming is when done properly, there's no side effects. In other words, you don't write code that changes memory at random. In other words, the functions have no state. They perform a computation and return the answer. Very easy to parallelize code like that because you don't have to worry about, there's no race conditions. There's no shared state. Things come in and things come out, but there's no shared variables. Knowing that there's no shared variables means you can make things parallel very easily. So basically, if I do this in a functional way, I wish I had time to explain this, invite me back. I could do it next year or whenever the next one is. But basically what we do is we say, do the sequences in parallel. It's just say, do these in parallel instead of doing sequentially. It's safe to do because it has no side effects. The performance is almost as good as the C# code, the reduction. So you get about 3.5 seconds, but it's usually if you're a functional programmer, it's very easy. Just throw in the parallel statements and it works you have much more confidence that it works. Okay, so that's it. Multi-core is the path for better performance. It's hard to do, so beware. Tool support is weak. Lots of experimentation because every sort of situation is different, and it's hard to prove that it's actually right when you're done. So you got to really think carefully about, did I do this right, and did I do it safely? And remember Joe's favorite equation. So parallelism, memory contention, and memory hierarchy and contention. So, all right. A couple book references. That's my email, and the materials are up online on my website. We done? Okay, cool. Thank you.